Alright, Navy Electricity Electronic Training Series Module 12, Modulation, Chapter 1, Part 2. Alright, the AM transmitter principles. In this section, we'll describe the method used to apply the voice signal's intelligence to a carry wave, or by process of the amplitude modulation. The AM transistor can be divided in two major sections according to the frequency at which they operate. Radio frequencies and audio frequency units. Radio frequency unit is a section of the transmitter used to generate the radio frequency carrier wave, as illustrated in Figure 137. The carrier that originates in the master or oscillator stage, where it is generated by a constant amplitude, constant frequency and wave. The carrier is not of sufficient amplitude, but it must be amplified in one or more stages before it attains the higher power required by the antenna. With the exemption of the last stage, the amplifiers between the oscillators and the antenna are called the intermediate power amplifiers, or IPA. The final stage, which connects to the antenna, is called the final power amplifier. Okay, master oscillator, your intermediate power amplifier, the final power amplifier, modulator, audio amplifier, master oscillator, intermediate power amplifier, modulator, and final power amplifier. The second section of the transmitter contains the audio circuitry. This section of the transmitter takes a small signal with a microphone, increases the amplitude with the almost amount necessary to fully modulate the carrier. The last audio stage of the modulator is applied with its signal to the carrier and the final power amplifier. In this way, intelligence is included with the radiated radio frequency waveform. The modulate wave. The frequency present in the signal can be conveniently presented by the graph of the frequency spectrum shown in Figure 138. In this graph, each individual frequency is portrayed as a vertical line. The position along the line at the horizontal axis indicates the frequency with the signal. Height of the frequency line is proportional to the amplitude of the signal. The radio frequency spectrum shown in Figure 138 shows that the frequency presented by the hydrodyne occurs between frequencies of 5 and 100 kilohertz. Figure 138 shows the radio frequency amplitude 5 to 100 gigahertz, 94 kilohertz, different frequency differences, and difference frequency, originals frequency, some frequencies, 100. Rating and energy audio frequencies discussed earlier in this chapter is not practicable. The hydrodyne principle, however, to make possible the conversion of the audio frequency signal intelligence of the 200 radio frequency signal with the intelligence can be radiated with it transmitted through space. Look at it again in Figure 138. The sum of the differences frequency located very near with the radio frequency signal, 100 kilohertz, while the audio signal is 5 kilohertz. Space considerably distance away. Because of the frequency separation, the audio frequency can easily remove the filter shook with it, leaving just 3 radio frequencies, 95, 100, and 105 kilohertz. These 3 radio frequencies are radioed through the space through the receiving station. At the receiver, the process reverse the frequency of the 95 kilohertz for the example of the heterodyne with a frequency of 100 kilohertz, and the sum of the different frequencies are again produced. The similar process that occurs between the frequencies of 100 and 105 kilohertz of the resonant frequencies 95, 105, and 5 kilohertz are filtered out, except the 5 kilohertz difference frequency. This frequency is identical to the original 5 kilohertz audio applied at the transmitter is retained and amplified. Thus, the 5 kilohertz audio tone appears to have been radiated through space from transmitter to receiver. In this process is described 100 kilohertz frequency is referred to as the carrier frequency. Some of the different frequencies referred to the side frequencies, and some of the frequencies appear on the carrier. Above the carrier frequency is referred to the upper side of the frequency. The difference of frequency appears below the carrier and is referred to as the lower side frequencies. When the carrier is modulated by voice and musical signals, a large number of the sum of the different frequencies are produced. Although some of the frequencies above the carriers are spoken collectively as the upper side of the band, all different frequencies below the carriers are also considered a group called the lower side band. If the carrier and the modulating signal are constant amplitude, and the sum of the difference of the frequencies will also be constant with the amplitude. However, the carrier with the side bands are combined with the signal impedance viewed simultaneously with the oscilloscope. The resultant waveform appears to be shown in Figure 139. The resultant wave is called the modulation envelope. The modulation envelope has the same frequency as the carrier. However, there is rise and fall of the amplitude with the conditional phase shift between the carrier and sidebands. This causes these signals to first aid and then oppose one another. The cycle variation amplitude of the envelope have the same frequency with the auto modulating. Voltage of the audio intelligence is actually contained in the space differentiating between the carrier and sideband frequencies. Upper sideband original carrier, lower sideband original audio signal modulated envelope. Figure 139 shows the formation of modulating envelope. Bandwidth of the AM wave. An ideal carrier of the wave contains the signal frequency occupied with a very little frequency spectrum, and the carrier amplitude with the modulated sideband frequencies are created both above and below the carrier frequencies called the signal. To use up a greater portion of the frequency spectrum, the amount of space with the frequency spectrum required by the signal is called the bandwidth of the signal. Bandwidth is modulated wave. This function of the frequency contained in that modulation signal. For example, the 100 kilohertz carrier is modulated at 5 kilohertz audio tone sideband frequencies created at 95 and 105 kilohertz. The signal requires 110 kilohertz of space in the spectrum. If the same of the 100 kilohertz carrier that is modulated with a 10 kilohertz audio tone sideband frequency will appear at 90 to 110 kilohertz, and the signal will have bandwidth of 20 kilohertz. Notice that if their modulation signal becomes higher and the frequency the bandwidth requires also becomes greater. As illustrated above, the example, the bandwidth of the amplitude modulated wave at the instant of the 2 times highest modulation frequency applied at the time. Those 400 kilohertz carriers modulated for 3 and 5 and 8 kilohertz simultaneously sideband will appear at 392, 395, 397, 403, and 405, 408 kilohertz. The signal appeared for the 392 and 408 and has the bandwidth of 16 kilohertz, twice as high as the modulating frequency of the 8 kilohertz. Musical instruments produce complex sound waves containing the greater number of the frequency. If the frequency produced by a piano, for example, the range is approximately 27 to 4200 hertz, and with a harmonic frequency extending beyond 10 kilohertz, modulating frequency up to 115 kilohertz, including the signal transmitted with the musical patch with a high degree of fidelity. This requires a bandwidth of at least 30 kilohertz to prevent actuation with a higher order harmonic frequency. If the signal to be transmitted contains a voice signal only, with the fidelity is a minor importance of the bandwidth requirement is much smaller. The barrier tone voices include the frequency up to 100 to 350 kilohertz or 250 kilohertz. Intelligible voice communication can be carried out as long as the communication system retains audio frequencies up to several thousand hertz. Compare the condition of transmitting voice signals with those transmitting musical review reveals that much less of the spectrum space required for the voice communication. Radio stations, the standard broadcast band, are assigned with the frequency carrier frequency for the Federal Communication Commissions. The 2 stations are located near each other. Other carriers must be spaced some of the minimum distance apart with the radio spectrum. Otherwise, with the sideband frequency of our station interfere with the sideband frequencies of other stations. The standard IAM broadcast band started at 535 kilohertz and into the 1,605 kilohertz. The carrier assignment starts at 540 kilohertz, continuing in succession 10 kilohertz increments up to until an upper limit of the broadcast band is reached. As a total of 107 carrier assignments or channels over the entire broadcast band with the station. If the stations were assigned to all 107 channels given the geographical area, each station would be allotted a channel width of 10 kilohertz. These 5 kilohertz on each side of each of the carrier with the sideband. Since the interference between them such closely spaced stations would nearly be impossible to prevent, the Federal Communication Commission avoids assigning adjacent channels to stations in the same area. Consequently, of this policy, one or more vacant channels normally exist between the stations and the broadcast band. In the interest of better fidelity, these stations are permitted to use modulating frequencies higher than 5 kilohertz as long as there is no interference with the other station produced. Analysis for the AM wave. The significant amount of information concerned with the basic and principal amplitude modulation can be obtained studied with the property of the modulation envelope. The carrier wave, which has been modulated voice of music signal, is accompanied with the 2 sidebands. Each sideband contains individual frequencies that are very continuously. Since the wave of this nature is naturally impossible to analyze, you can assume that the following section of that modulation signal, unless they are otherwise qualified, signal frequency constant amplitude sim wave. Percent of the modulation AM wave. The degree of modulation is defined with the terms of maximal permissible amount of modulation. The fully modulated wave is said to be the 100% modulated envelope in Figure 140. View A show the condition of the 100% sim wave modulation. For the degree of the modulation, the peak audio voltage must be equal to the DC supply voltage to the final power amplifier. Under these conditions, the radio frequency output voltage will reach 0 on the negative peak of the modulating signal, and the positive peak it will rise twice as the amplitude of the unmodulated carrier. Alright, conditions of 100% modulation. Unmodulated carrier amplitude. Section A show the maximum radio frequency voltage twice of the voltage of the carrier. radio frequency output is 0 at this instance. When analyzed, the modulation envelope consists of the unmodulated radio frequency carrier voltage plus the combined voltage of the two sidebands, the combined of the sideband voltage of approximately equal to the radio frequency carrier voltage. Each sideband frequency contains one half of the carrier voltage, as shown in view B. The condition is known as 100% modulation. The maximum modulation radio frequency voltage is twice the carrier voltage. The auto modulation voltage can be increased beyond the amount required to produce 100% modulation. What happens is negative peak of the modulation signals between large amplitude and then the DC plate supply voltage of the final power amplifier. This causes the final plate voltage to be negative for the short period of time near the negative peak of the modulation signal. For the duration of the negative plate voltage, no radio frequency energy is developed across the plate tank circuit. The end of the radio frequency output voltage remains at 0, shown in Figure 141, View A. Alright, Figure 140B shows the condition 100% modulation. The carrier in between the frequencies of the sideband frequencies is one half the carrier amplitude. Alright, the unmodulated carrier amplitude maximum radio frequency voltage is greater than twice the carrier voltage. The radio frequency output remains at 0 in a finite period of time. Look carefully at the modulation envelope in View A. Show the negative peak over the modulation signal will effectively be limited with the signal with a demodulated detector. The receiver would be an appearance that's somewhat similar with a square wave. The condition known as overmodulation causes the signal sound severely distorted, although that will depend on the degree of the overmodulation. Overmodulation will generate unwanted spurious sideband frequency. This effect can easily be detected by tuning the receiver, but somewhat outside of the undesired frequency. You would likely to be able to tune one or more of the undesired sideband frequency. The reception would be severely distorted, possibly unintelligible without overmodulation. No such unwanted sideband frequencies would exist. You would be able to tune only the desired frequency. The unwanted frequency will appear with a considerable range both above and below the desired channel. The effect is sometimes called splatter. Spurious frequency shown in View B of the cause of the interference with the other station operating with the adjacent channel that should be clearly understand the overmodulation intended distortion and interference is to be avoided. 141 should be show the overmodulation continue. The desired side frequency, the carrier, these are spurious frequencies generated as a result over the modulation, the next to the side bands. In addition, with the above problem for the overmodulation also causes abnormally large voltages. The current exists at various points within the transmitter, therefore sufficient overload protection. Circuit breakers and fuses should be protected with the protection not provided with the excessive voltage causing the arcing between transformer windings between plates of capacitors, which will permanently destroy dielectrical material. Excessive currents can also cause the overheating of the tubes and other components. Ideally, you want to operate the transmitter at 100% modulation so that it can provide with the maximum amount of energy in the sideband. However, because of the large and rapid fluctuations in amplitude of these signals, normally obtaining the ideal connection is seldom possible. When the modulators are properly adjusted, the loudest part of the transmission will produce 100% modulation. The quieter parts of the signal then produce less degree of the modulation. To measure the degree of the modulation less than 100%, you can use the modulation factor M to indicate the relative magnitude of the radio frequency carrier and the audio modulating signal. Numerically, modulation factor is equal to the peak-to-peak of the root mean squared value of the modulating voltage over the peak-to-peak, the voltage peak-to-peak. To illustrate the use of the equation, assume the carrier wave of the peak amplitude of 400 volts is modulated by a 3 kilohertz sine wave of the peak amplitude at 200 volts. So the modulation factor would be your peak-to-peak amplitude would be 200 over the peak-to-amplitude voltage is modulated for 0.5. Modulation frequency multiplied by 100%. The resultant frequency would be percent of the modulation. Percent of the modulation would be 50%. By using the correct equation, you determine the percent modulation for the modulation envelope. The method useful when the percent of the modulation is to be determined, you use the parameter of the screen over the oscilloscope. For example, assume that the oscilloscope is connected to the output of the modulator circuit produced for the screen pattern shown in Figure 142. According to the setting of the calibration control, each for the larger division of the vertical scale is equal to 200 volts. By using this scale, you can see that the peak circular carrier amplitude unmodulated portion is 400 volts. The peak amplitude of the carrier is designed at EO. In figure, show that the peak amplitude of the carrier is EO. The voltage max, voltage minimum, each division at 200 volts. So your modulation factor is percentage. Your modulation per factor. Modulation factor is equal to 100 volts. So your modulation factor is percentage. Your modulation per factor. Modulation factor is equal to 100 volts. So your modulation factor is percentage. Your modulation per factor. Modulation factor is equal to 100 volts. So your modulation factor is percentage. Your modulation per factor. the percent of modulation is equal to the voltage max over the voltage minimum over 2 times the peak amplitude of the carrier times 100, and the amplitude of the auto modulating voltage can also be determined by the amplitude variation in the envelope pattern. Note that the peak-to-peak variation in the envelope amplitude, the voltage max, voltage minimum is equal to 400 volts on the scale. Note that the peak amplitude of the audio voltage is 200. If these radio frequency audio voltage values are inserted into this equation, the pattern figure 142 is found to represent 50% modulation. If the voltage modulation versus the voltage, what was that? Voltage peak to peak. In the equation, assume to represent the peak-to-peak value formula result of the percent of the modulation is equal to the voltage. Once again, the peak-to-peak, the root mean squared moderating voltage, and over the peak-to-peak. And monitoring voltage over the peak-to-peak and times the amplitude, you get since the peak-to-peak voltage is EM, the figure EM max over minus minimum substitute. Since the peak-to-peak value of the carrier is 2 times EO, would substitute EO for EC following lines. Alright, your linear vertical distance represents the voltage on screen cathode ray tube. Vertical distance can be used in place for the voltage equation. Thus, the only percent of the modulation required for the oscilloscope need to be calibrated. Actual circuits are not required in Figure 142. The voltage maximum is represented 600 volts with 3 large divisions, and voltage minimum to 1 division, and your EO. 400, 200 division equation, a division and screen pattern configure the percent of the modulation. Alright, percent of the modulation equals 3 minus 1 over 2 times 100, or 50%. With the EO equation, the difficult measure of the alternative solution can be obtained with the equation percentage of the maximum voltage minimum over voltage maximum plus voltage minimum times 100. Alright, vertical analysis for the AM wave. You studied earlier synaptic the modulation envelope result of the instantaneous sum of the carrier sideband voltages are collided with respect to the time and tempo to add the three voltage point to point would prove that to be a huge task. Same end of the result can be obtained by the rotating vector to represent each of the 3 frequencies. Constant envelope of the following analytic vectors will be scaled to indicate the peak of the voltage value of the frequency that represented the analyst has been simplified further by using the frequency at 8 Hz to represent the carrier frequency. Each cycle of the carrier requires 1/8 of a second to complete 360 degrees. The carrier will be 100% modulated by the sim wave having a frequency 1 Hz, thereby producing a sideband frequency of 7 and 9. Envelope development from factors: modulation signal, upper sideband carrier, lower sideband waveforms illustrated in view A through D, respectively. Figure 143. Note that the vertical lines passing through the figure divide each of the waveform into segments of 1/8 of a second. Each of these lines coincide with the starting of the endpoints of each cycle of the carrier wave. Modulating signal 1 CPS, upper signal CPS, carrier CPS, sideband CPS, peak voltage envelope. Modulation envelope 1 second. For modulation envelope addition with the vectors representing the carrier and sidebands. During the first 1/8 of a second of the turn from time 1 to 2, the carrier will completely exactly 1 cycle at 360 degrees shown view C. Upper sideband has a frequency of 9 Hz will complete each of the less than 1/8 of a second. Therefore, during the timer curve of the carrier with the complete 1 cycle over the 360 degree, the upper sideband view B is able to complete 1 cycle of 360 degrees plus an additional 45 degrees the next cycle with a total of 405 degrees. Lower sideband view D, the frequency of 7 Hz cannot complete with the entire cycle of the 1/8 of a second during the time when the interval required for the carrier wave to progress through the 360 degree. The lower sideband frequency 7 Hz can complete only 315 degrees, 45 degrees short of the full cycle. Keeping the factors in the mind, you should be able to see that the phase angle between the 2 sideband frequencies between each sideband frequency for the carrier frequency will continually shift at the instant for the time band 3, but the carrier sidebands will be phased the view E, the view E, through causing the envelope amplitude view F to be twice the amplitude for the carrier. Another instant for the time 7. Those sidebands are out of phase for the carrier view E, but cause the complete cancellation of the radio frequency voltage envelope amplitude will be 0 at this point. You should see that although the carrier sideband frequencies have the constant amplitude with every changing phase. The difference between these causes modulation envelope to vary continuously in amplitude. Vector analysis of the modulating envelope will develop with the aid of Figure 144. With the Figure 144 view A, the vertical vector C has been drawn representing the carrier of the waveform Figure 143 at the time interval 1, Figure 143. Upper and lower sideband frequencies are opposite phase with respect to each other and 90 degrees out of phase with respect to the carrier. In addition, illustrating Figure 144 view A, the sidebands vectors U and L drawn in the opposite direction along with the horizontal axis signs of the upper sideband U is equal to amplitude but opposite of the phase of the lower sideband L. The two sidebands voltage can cancel one another. The amplitude of the envelope at the time 1 is equal to the amplitude of the carrier. Same vector diagram shown in smaller scale in Figure 143 view E. Figure 144 view A, vector diagrams time interval 1 and 2. C is the carrier, L is the lower sideband, U is the upper sideband. Alright, during the 1/8 of the second time, the interval between time interval 1 and 2, the three vectors rotate counterclockwise direction, velocity determined with the respective frequency of the vector represented by the carrier, for example, that has made one complete rotation 360 degrees back into its original place, shown in Figure 144 view B. Upper sideband frequency, however, will complete 405 degrees in the same 1/8 of a second. Notice for the view B, the vector U must be made one complete counterclockwise rotation 360 degrees plus 45 degrees for the total rotation of 405 degrees. Vector L represents the lower sideband rotated with velocity less than either the carrier upper sideband. 1/8 of the second vector L completes only 315 degrees, which is 45 degrees short with the one complete rotation. At the end of the 1/8 of a second, the three vectors advance to the position shown in view B. Alright, resonant factor between L, U, and C. Continuous at time interval 2, the vector diagrams at time interval 1 and 2. The resultant vector of the view B was obtained with adding the vector U and L and U to vector L. Since each sideband has 1/2 the amplitude of the carrier, the two sidebands differ with the phase of the 90 degree for the amplitude of the resonant vector can be computed with a computation not shown would show the resonant vector to have amplitude that is approximately 70% of that of the carrier. Thus, the time interval 2 has the amplitude of the modulation envelope with 1.7 times the amplitude of the carrier. This is condition shown in Figure 143 view F. But a similar proof of the vector diagrams can be constructed with the time intervals T3 through T9. This is done by the Figure 143 view E, but these 9 individual vector diagrams complete the modulation envelope of Figure 143 view F that can be constructed. Note the particular vector diagrams for T3, T7, at T3, all three waves, therefore all three vectors are in favor of the modulation envelope, and in this instance, therefore, be equal to twice the amplitude of the carrier, since E for the sideband frequency 1/2 of the amplitude of the carrier. Time interval stand T7 and 2 sideband frequencies are in phase with each other, 180 degrees out of phase for the carrier with the cause of the combined sideband voltage to cancel the carrier voltage modulation envelope between become 0 over the instance. Note that the transmitter output is to be 0 for that 2 T7. Both the carrier and sideband frequencies must present. If any of the three frequencies were missing, complete cancellation would not occur. Radio frequency energy would be present in the output. Although the vector analysis was made in frequencies 7 and 8 and 9 Hz, the same description could apply with the frequency actually present with the output of the transmitter. Alright, modulating level of the AM wave. As stated earlier, the modulating signal could be introduced into the active element of the tube at the position with the various assignment arrangements possible a single stage, and the modulation signal can also be applied with any of the radio frequency stage of the transmitter. For example, the modulation signal can be applied to the control grid or plate of one of the intermediate power amplifiers. The modulator circuit is usually placed in one of the two categories, high or low level. Modulation circuits are categorized according to the level of the carrier wave at the point of the system where the modulation is applied. The Federal Communication Commission defines high-level modulation in the Code Federal Regulations as modulation produced in the plate circuit that is the last radio stage of the system. The same document defines low-level modulation produced in an earlier stage than the final. Modulation system. To complete the understanding of the AM modulation, we are now going to analyze the operation of the typical plate modulator. The detailed circuit descriptions will be to give the understanding of the basic AM plate modulator. In addition, we'll cover the basic circuit, the description of the cathode grid electronic tube modulators, base emitter with the collector transistor modulators in this chapter. Alright, the plate modulator. In Figure 145 of the basic plate modulator, circuit of the plate modulation permit for the transmitter to operate with a high frequency, simple to the modulator available, and also easy to adjust for the proper operation. The modulator is coupled to the plate circuit with the final with the radio frequency amplifier through modulation transformer. 100% of the modulator must supply enough power to use Call for the plate voltage of the final radio frequency amplifier to vary between 0 and 12 the DC operating place voltage. The modulator tube V2 is the power amplifier based on the operating class of the A1. The final radio frequency power amplifier V1 is based on the nonlinear portion of the operating range of the Class C that provides the efficient operation of the final radio frequency power amplifier V1 produces the necessary heterodyne action between the radio frequency carrier and the audio frequency modulation frequencies. Alright, this shows the transmitter, transistor 1 and 1, unmodulated radio frequency input through the capacitor, amplifier, final radio frequency power amplifier, modulation radio frequency amplifier, cam capacitor, transmitter, audio modulation signal, resistor, modulator. V2 was your the modulator tube, and transmitter 2, transformer 2, modulation power supply, and FBA power signal. Your plate modulator circuit operation figure 146 view A through E show the waveforms associated with the plate modulator circuit shown in figure 145. Refer to these two figures throughout the following discussion. Equivalent of the power and the amplifier of the voltage plate supply voltage supply with the V1 control grid, radio frequency plate current, total plate voltage, modulated radio frequency off the tank circuit. Alright, your radio frequency power amplifier V1 acts as a class C amplifier, no modulation present in the plate with the circuit of the V2 that is modulated with transfer of the modulating voltage to the plate with the volt mounted power radio frequency power amplifier. Let's see how the circuit produces the modulated radio frequency output. View A show the figure 146 show the plate supply with the voltage over the power amplifier or radio frequency power amplifier constant DC voltage at the time of the time 1 with no modulation signal applied with the voltage radio frequency power amplifier is based to cut off at the time the incoming radio frequency carrier. View A is supplied with the grid of the radio frequency power amplifier transistor time 1. Called the plate circuit can be current, pulse, or surge, and each time of the grid is driven in positive with the radio frequency pulse referred to the current pulse as shown in the view. Plate tank circuit output circuit check with the oscillation B with the current pulse of the radio frequency output wave shown in view E with the develop the radio frequency plate voltage waveform and shown in view D. An auto modulating voltage applied with the grid of the V2 with the amplified with the grid. The grid of the V2 is amplified by the modulator coupled with the plate with the V1 amplifier and modulation transformer. The second of the transformer 2 is interior with the plate supplied with the voltage E of the radio frequency power amplifier with the modulating voltage with either V2 track with the plate with the voltage with the radio frequency voltage amplifier. Power amplifier. This includes the twice the normal value of the radio frequency plate current that can be both the double as shown that you see with its time of the view in 3A with the supply voltage reduced to 0 with the radio frequency plate current decreased with the 0 that's shown that you see with the change of the radio frequency current called with the radio frequency tank. T3 voltage at double the time 2 with the increase 0 to time 3 with the shown view E with the action result of the modulation envelope shown view E representing 100% modulation for the transformer coupled out with the tank circuit of the transformer to the antenna because of the oscillating action with the tank circuit of the transformer T3 the voltage and radio frequency voltage power amplifier has been rated to handle at least 4 times its normal plate supply voltage as shown plate voltage waveform view D. Heterodyne the auto frequency intelligent with the modulator V2 will carry the end of the plate with the circuit of the final power amplifier V1 require the large amount of the auto player. All the power of the voltage contained with the intelligent must come from the modulator state. This is why modulation is called high level modulation. Heterodyne action plate modulator effectively change with the auto frequency different part of frequency spectrum. The action allow the antenna equipment over the practical side of it to be used with the transmit intelligence. Now let's look at several of their type of modulators. Your collector injection modulator. The collection injection modulator, the transistor equivalent with electrode tube, the AM plate modulator, transistor modulator can be used with a low level to relatively high level of modulation, referred to as the relatively high level of modulation because of the present time of the transistor located limited in their power handling capability, illustrated in figure 147. The circuit design, the transistor collector injector modulator is very similar within those of the plate modulator. The collector injection modulator is capable of 100% modulation with medium power handling capabilities. And show the radio frequency resistor input with a transformer winding in L1 and L2 induction current, resistor capacitor tuning circuits, resistor 2, Capacitor 2 and 3 resistor resonance circuit. Transformer 1 capacitor, induction 3 output. Audio frequency modulation through transformer 2, the inductor 1 and 2 and 3, capacitor 3, voltage collector. In figure 147, the radio frequency carrier is applied with the base for the modulator transistor 1. The modulating system is applied with the collector with the shear with the collector with supplying with the voltage through the transformer 3. The output with the taken from the secondary transformer winding. Non-modulating signal with the transistor 1 acts as the radio frequency amplifier carrier with the frequency with the modulation signal applied with the add and subtract with the collector supply voltage. This called the radio frequency current. Pulse for the collector, verify the amplitude of the collector, supply voltage of the collector, current called the current pulse, this is the, called the oscillation of the tank circuit with the capacitor 4, and primary transformer 2 winding, the tank circuit is tuned to the carrier frequency during the period of the collector current is high, the tank circuit oscillates strongly. At the time of the current, collector current is small, but the entire absent with little no energy supplied with the tank oscillation becomes weaker dial. The modulation envelope is developed as with it is a plate modulator. Alright, your transistor technology continues to develop a higher power application. The transistor collector injection module will be employed. Plate collector injection module are mostly commonly the type of the modulation because the modulation signal can be applied with the final stage of the radio frequency amplification. This allows the majority of the radio frequency amplifier stages to be operated at Class C for the maximum efficiency of the plate and collector injection modulators also require large amounts of modulation power since the modulator stage must apply with the power contained in the sidebands. Alright, your control grid modulator. Incapable of use of the minimum of the audio frequency modulator power is desired with the form of level low modulation necessary for the control grid modulator to use the widely portable mobile equipment to reduce the size of the power requirements usually with extreme high power wideband equivalent equipment such as the television transmitter high level plate modulation and the difficult costly to the achieve figure 148 the basic schematic with the type of typical control grid of the modulator. Our control grid modulator, you see the radio frequency drive and then radio RFC 1, radio frequency current 1, radio frequency amplification V1, radio frequency audio frequency modulator, audio frequency input, transistor 1, capacitor tuning circuits, Alright, the control grid modulator using various grid bias for the frequency modulating signal to vary with the instantaneous plate voltage of the current. These variations the cover the modulation of the carrier with the frequency entry with the coupling capacitor. Alright, the modulating frequency of the entry with the grid bias with the transformer 1, the modulating signal increase with the decrease with the positive negative that will add with the subtract from the bias with the radio frequency amplifier voltage V1. The change in bias with the cover with the corresponding change of the plate voltage of the current. These changes in plate voltage current with a vectorally with the carrier of the frequency provide modulation envelope the same fashion as dealt with the plate modulator. Same as the change of the plate circuit with the radio frequency amplifier control provide these changes in the grid by with the gain, but these two frequencies require only low level modulation signal, even with the input signal at the low level. The oscillation modulation voltage peak will occur with these called with the radio frequency amplifier to saturate this occur with the distortion output, but the carrier must be taken with the bias for the radio frequency amplifier tube to maximum power output. Will maintain minimum distortion power develop the modulation envelope cause comes from the radio frequency amplifier because the radio frequency amplifier has to be capable of supplying additional power that is based on the entry within the carrier frequencies at much lower output level than its rating. This is reducing the efficiency necessary during non-modulated period to provide the tube with the power developed with the sidebands compared with the plate modulation grid modulation less efficient produce more distortion. Radio frequency power amplifier supply all the power with the output signal grid modulation has the advantage but no regard not requiring much power from the modulator. Alright, basic injection modulator. Basic injection modulator, some of the control grid modulator electron tube, the circuit that uses to produce the low level of modulation equipment that over operating very low power levels. In figure 49, the bias for the transistor 1 establishment voltage divider, resistor 1, resistor 2, the radio frequency carrier, input transformer 1, no modulating signal. The circuit acts as the standard radio frequency amplifier modulating signal injected the capacitor and 1 to develop the voltage across resistor 1. Adds or subtract the bias of the transistor 1, then chamber the bias, the chamber the gain with the transistor 1, causing more or less energy to be supplied. Collector tank circuit, the tank circuit develop the modulation envelope with the radio frequency and audio frequency modulator frequencies are made for the collector signal circuit. Again, this action is identical to the plate with the modulator. Our figure 149 shows the base injector modulator, radio frequency input for the transistor 1 going into transistor, transformer 1 going into transistor 1 through the capacitor induction circuit. Your tank circuit, also radio resistor 1, capacitor, resistor 3, resistor 2, your tuning resonant, your resonant circuit, audio frequency input with capacitor 1, resistor 2, voltage. Alright, because extremely low-level signal produced the modulation of the bass injector modulator was suited with a small portable equipment and walkie-talkies test equipment and cathode modulator. Another low-level modulator with a cathode modulator generally employed where the audio power is limited with the distortion modulated circuit can be allowed. The cathode modulator vary with the voltage cathode to for the modulation envelope. Send the cathode and see for the grid plate circuit that you should be able to see for the cathode voltage with effectively change the voltage of the other tube elements to properly control the voltage of the tube. You can call the cathode modulator operate the form of the plate modulation high intensity. Usually the cathode modulator is designed to perform about the midway between the plate and plate grid modulator levels. You have the advantage of either type of the operator between the two levels. The modulator provides a more linear output with a moderate efficiency modulus output requirement, audio power requirement. Figure 150, the radio frequency carrier is applied with the grid of the radio frequency amplifier modulating signal is applied with the shear of the cathode of the transformer 1 signal and the modulating signal efficiently within shear of the grid on the plate with the voltage level. The modulating voltage required will be determined by the relationship of the 3 volts of the modulating taking the plate with the plate circle with the plate with the tank of the developing in the modulation envelope. You should just did it as the plate modulator. Alright, show the 450, show the cathode modulation audio frequency input going into the modulator transformer 1 the capacitor 1 resistant grid radio frequency RFC and radio frequency input driver. Alright, emitter injector modulator. The transistor equivalent with the cathode modulator of the emitter junction modulator. Same care for the basic injection modulator discussed earlier. In its extreme low level, the modulator is useful with the portable equipment. The emitter injection modulation gain radio frequency vary with the changing voltage of the emitter. The change voltage is coupled by the injection modulating signal with the emitter with the circuit of the transistor 1 shown figure 151. Modulating voltage adds and subtracts for the transistor by the change of the bias caused by the change in the collector current resulting in heterodyne action. Modulation envelope that developed across the collector tank circuit. Figure 151 shows the emitter injection modulation. Radio frequency input going on transistor 1, double input, double output, transistor 1, transformer 2, carrier capacitor, resistor 3, capacitor 2, tuning circuits, resistor 1 and 2, capacitor 2. You have to study the 6 methods of the amplitude modulation. Now that these are not the only methods available, but they are most common. Although all the methods of the AM modulation, same theory with the heterodyne across the nonlinear device. AM modulation is one of the easiest, way less expensive type of the modulation to achieve. The primary advantage of the AM modulation are subjectively to the noise interference and the interference of the transmitter powers is weighted in the transmission of the carrier frequency because it contains no AM intelligence. In the next chapter, you will study other forms of modulation that have been developed to overcome these disadvantages. Chapter 1 Summary.